All right, so let's pick up where we left off in the last video, and we're going to talk about how to use that matrix that we already created for points A, B, and C to demonstrate 4 different types of translations. So let's take a look. I've rearranged our screen a bit so that it's just a little bit more, a little less spread out. I guess that's what I'm going for. And I want to talk first about translations. So we said that a translation is just a slide of a figure. So that's a slide. We take a figure and we move it. It doesn't turn. It doesn't change shape. It doesn't change size. It just moves. That's all it does. So let's say, for instance, and actually I'm going to let you take a look at your worksheet number 2, which says, the directions say, find the coordinates of the image under each transformation. Express your answer as a matrix. And then it says for number 2, to perform a translation of 1 unit right. I'm going to write that down. 1 unit right and 4 units up. So let's look at this in the actual figure. If we come over here and we take each point and we slide it, let's say 1 to the right, we'll start with A, 1 over, and then 4 up, 1, 2, 3, it's going to be right up here, 4, which is actually the point 5, 6. And then we take B and we move it over 1 unit and then up 1, 2, 3, 4 units. So that's now 0.52. And then we take C and move it 1 unit right and then 4 units up. 1, 2, 3, 4. So that's now negative 2, 4. Oops, that's a negative 2, 4. If we connect the dots, we moved each point separately, but we get a figure that has been translated or just slid 1 unit to the right and 4 units up. And that's that. That's all that there is to this, geometrically speaking. Now, the instructions for your homework asked you to take this and write the answer as a matrix. So I will do that. I'm going to write it in the same order that we did before. Actually, usually when we slide something, we call, this is kind of just a side note, we usually call it A prime. That means I've taken A and I've moved it once. And then I call B prime and C prime. So you don't have to use that. That's geometry language, but why not throw it in here? Because it's kind of useful. So we can see that A is no longer 4, 2. It's now 5, 6. B is no longer 4, negative 2. It's now 5, 2. And C is no longer negative 3, 0. It's now negative 2, 4. And what I want you to see is that we actually just drew this whole picture out, but we could have actually done this much more easily by saying, okay, everything in the top column is an X. And everything in the bottom, or not in the top column, sorry, the top row is an X. And everything in the bottom row is a Y. Now we're going to take each of these points and move it 1 to the right and 4 units up. So we could have actually just said, okay, every X value is going to increase by 1. That's what happens when we move to the right. We add 1, add 1, add 1. Now compare this. 4 plus 1 is 5. 4 plus 1 again is 5. Negative 3 plus 1 is negative 2. So what do you know? We actually could have done this much more easily using the data from our matrix instead of drawing the whole picture out, which is fine. We can do that. The matrix gives us a little bit of like a cheat to make this a little bit easier, a legal cheat. Let's go see what happens with when we move each of the Y values 4 units up. So if we are going 4 units up in the Y direction, we add 4. So add 4, add 4, add 4. And what we get for the first is 2 plus 4 is 6. That's what we got. Negative 2 plus 4 is 2. And 0 plus 4 is 4. So lo and behold, we find that the information for for the matrix we could have done without graphing. That's basically the bottom line. So that's how we use matrices to perform a translation. Okay, we're going to pause this for a second, then we're going to keep going. We're going to clear the board and try this with a dilation. Okay, now we're going to talk about dilations. And a dilation is when we cause something to either grow or shrink. Things that grow, we can multiply by what we call a scale factor. That's just the terminology we use. That is greater than 1. So if I have a scale factor that is greater than 1, then something will grow. And if I have something that is less than 1 but greater than 0, so in other words it's still positive but it's less than 1, so that's like fraction quantities. So what should I call this? We'll say the factor is greater than 0 and less than 1. That will cause it to shrink. So here are a couple examples. Like if I were to multiply something by 5, it would cause it to grow 5 times bigger. If I were to multiply it by 1/5, it would cause it to shrink. So when I talk about growing or shrinking, just keep in mind those are examples. Okay, let's look at your worksheet again. Let's look at number 3, which asks you to do the same thing to find the coordinates of the image under each transformation, in this case a dilation of 1.5, and then express your answer as a matrix. So instead, last time I had you perform the translation kind of visually using the graph and then write your answer, but I'm going to show you this time. I think it's easier to do it the other way around, to actually find what happens when we make this grow by a factor. Our factor is 1.5. We want to dilate by 1.5. So we're going to use the matrix and then we're going to graph it afterwards. So let's say we take this matrix, 4, 2, 4, -2, -3, 0, and we want to dilate it by 1.5. That means we want it to grow 1.5 times its current size. What I do is I just take the data in the matrix and I multiply it by the scale factor. I multiply it by 1.5. That's it. Well, that's 1.5, not 15. What does that mean? Well, we already know that we can use scalar multiplication kind of as like, we're like sharing like the distributive rule, 1.5 times each element. So let's see what we get. 1.5 times 4 is 6 because it's 1.5. So 4 plus half of 4 is 4 plus 2 is 6. Same here for the 1.5 times 4 again. 1.5 times -3 would be -3 and -1.5, so that'd be -4.5. You can, of course, do this in a calculator too, but I like doing math in my head because it's faster. 1.5 times 2 would be 2 and 1, that would be 3. Times -2 would be -3. And 1.5 times 0 is 0. So let's see what happens. What we now have is we have the information for A prime, B prime, and C prime, or in other words, A, B, and C of our dilated shape. So going back to our graph, let's graph A prime, which is 6, 3. So I'm going to go out 5, 6. I know they didn't give you all the room that you could really use here. There's our point A prime. I guess I should write that. B prime, 6, -3. So same thing, come out here, except we're going to go down to -3. That's B prime. So we just graph this point. And then lastly, we'll graph -4.5, 0. So we go out to 4.5, -4.5, and 0. And that's C prime. And then check out, if we take this and connect the dots, we get a rectangle, a triangle that has grown by a factor of 1.5. And how do I know? I mean, that'd be a tough thing to just figure out on our own without the help of a matrix. But we know that we've actually made it grow that much because we've changed each aspect of the coordinates by that factor. We've multiplied it by 1.5 and it grew. Now, if I wanted to dilate this to make it shrink, I could have multiplied it, let's say, by 0.5, so 1/2. And what that would have done is have it shrink so that it would be smaller than the original. But we perform our operations the exact same way. Either we multiply it by a number greater than 1 and it grows, or we multiply it by a number less than 1 and greater than 0 and it shrinks. So that is our second type of transformation. All right, we're going to pause again, and then we will continue with, we'll do reflections next. Okay, so let's talk about reflections. Reflections, there are all kinds of reflections. I could reflect across the y-axis, which would mean that I'd take, let's say, A, instead of being 4, 2, I would reflect it across and it would be -4, -2. And I could take B, and instead of being 4, -2, it would be -4, -2. And then I could reflect C to the other side, which would put it right here. And if I connect the dots, I'm just doing this quickly. This is not specifically in your problems 1 through 11, but that's an example of a reflection. I could also take this figure and I could reflect it over the x-axis. That would mean like reflect it like this across the horizontal axis, but whoops, I'm just going to highlight that, like across this line. If I did that, A would reflect across to B, B would reflect up to A, and C would stay the same. So that wouldn't be a very interesting picture, but it is something I could do. Now in your homework, or in your packet, number 5 asks you to make a reflection across the line, or it says a reflection in y equals x. So you might be wondering, what does that mean? A reflection, and we always say a reflection in because it's like a mirror. So a reflection in y equals x. Well, y equals x is a line, right? This is sort of like y equals mx plus b. It'd be y equals 1x plus 0 if we put it in y equals mx plus b form. So that means we have a y-intercept of 0 and a slope of 1. I guess that should be y equals mx plus b, not 0. So that would mean it would be the line that has a y-intercept of 0. Oops, let me just do this a little bit more easily. And it's going to go up 1 over 1, up 1 over 1, up 1 over 1. So it's this diagonal line. So that's what question number 5 is asking you to do, to reflect it across that line. Now, literally speaking, what this is saying is we're going to make a reflection by making y become x and x become y. Let me show you what I mean by that. We know that the first coordinate is 4, 2. Well, if I reflect it across this line, we actually are going to find the point 2, 4. If you don't believe me, check it out. 2, 4 is right here, and it's just perfectly across the line from our point A, is as a reflection. Same thing with B. We know that B is 4, -2. So let's find the point -2, 4. Where is -2, 4? That would be over here. -2, 4. Again, why am I doing this? Because I know that a reflection in y equals x means that I'm making y become x, making y equal x, and it means I'm making x equal y. So I would move that over there. And then C, which again, if you check, that's a nice perfect reflection across the diagonal line. And then C we know is -3, 0. So let's find the point 0, -3. And that would be right here. Again, check it out. It's a nice perfect reflection. Now let's see if I can connect all these red dots, which are my secondary points, my prime points. Oops. Make sure I connect the dots nicely. So this new, I'm actually going to kind of color it in here. this new triangle, check it out here, whoa, scribble everywhere, is a reflection across that diagonal line. And I was able to quickly do it by saying that each point, a reflection in y equals x, is going to turn y into x and x into y. Well, look how I can do that simply using a matrix. I could take each x and y and just flip the values. Make y equal x and make x equal y. And what happens when I do that? I get 2, 4, negative 2, 4, 0, negative 3. Now, do those values look familiar? Yes, they do. They correspond with the points that we see in our graph. So this is an example of a type of reflection using matrices, and how just by putting that information into a matrix, we're able to simplify. Okay, pause one more time, and then we're going to stop with rotations. Okay, lastly, let's talk about rotations. Rotations is where we take a shape and we just turn it. Now, if you look at number 6, it asks you specifically to rotate your figure 270 degrees. Now, if you don't remember from geometry, if you have a full rotation, that's 360 degrees. We can divide that. We usually rotate counterclockwise, especially as we get into talking about pre-calculus. So I'm going to use counterclockwise as the direction for our rotation. So that's why I drew the circle the way I did. So 360 is a full rotation. If I were to split that into 4 pieces, a quarter of a turn would be 90 degrees. A full or a half turn would be 180 degrees. We use those terms a lot, right? So 90 we know is a right angle, which is true here. If I had a little thing that was turning around, it would be turning 90 at the quarter mark. 180 we know is like a full turn, like if we say, oh, that person did a 180, means they turned all the way around. They were facing one way, now they're facing the other. And then 270 is like a 3/4 turn, and then we said 360 is a full. So when we're talking about 270, that means that I want to take like A, and I want to rotate it all the way down like a 3/4 turn. Is that about right? Kind of, sort of. And the same thing, we want to take B and do the same thing, and C and do the same thing. So first, I want you to picture if I were to move this 90 degrees, this point, instead of being at 4, 2, would actually be up at 2, 4. It'd be over here, and then B would be over here. I'm going to draw it out. This would be, if I took this side right here, and I moved it 90 degrees, it would end up over here. If I moved it 180, it would end up over this way. And if I move it 270, it's going to end up down here. So this is ultimately, we'll do a little star. This is ultimately where we want it to be, because number 6 says do a 270 degree rotation. So check that out again. We have our original AB, we did a 90 degree, a 180, and then a 270. That should make it easy to figure out where the C is. If this is where the line, the AB line is, then C is going to be up over here. And we can fill in this triangle, shade it in again, and we can see that we've rotated it 270 degrees counterclockwise. Okay, how does that look in a matrix? Well, how would we write out, this would again be A prime, B prime, C prime. Well, A has rotated all the way around to here, right? It's moved from here to here to here to there. B has moved to the spot B prime, and then C has moved here to C prime. So filling that data in, we have 2, negative 4. For B, we have negative 2, negative 4. And C has moved to 0, positive 3. Now, and that's it. That's our answer. But again, I want you to see, kind of as our final place that we're going to end our talk about transformations, and also about using matrices to store and to store data, and also to make it easier for maybe a computer to perform more complex operations. This is what I want you to notice. What we just did was kind of maybe a little tricky even for some of you. For some of you, doing visual manipulations is so easy, but what I've learned being a teacher of geometry in the past is that some people love that stuff. Some people really, really don't like it. I really think that some people naturally have like a three-dimensional thinking kind of brain that likes to flip things around, and some of us just don't. That's not how our brain works. So some of us can get really tripped up trying to move stuff like that around. But look at the pattern that we actually could apply once we learn a pattern. Look at the pattern that matrices allow us to, or how it allows us to do this more simply. So for instance, the point 4, 2, if I look at A prime, it flipped the x and y and then turned the y negative. So that's interesting. So 4 and 2 became 2 and 4, but the y became negative. Let's see if that repeats itself. For 4 and negative 2, that becomes negative 2 and that would flip negative 2 and 4, but then the y becomes negative. So the same thing happens. We flipped the x and y and then turned the y negative. And then lastly, we have x and y. If we flip negative 3 and 0, it becomes 0 and negative 3, but then we make it negative, which would be negative negative 3. That's positive, so it becomes 0 and 3. So the pattern we found is that rotating 270 degrees is the same as flipping x and y. So we switch the x and y, and then we make y negative. Or we flip the sign. If it's negative, we make it positive. If it's positive, we make it negative. So think about how valuable that information might be if I am a computer, right? Because computers are ultimately kind of dumb. Right? They only understand really, really, really basic commands. That's why we have all these, like the classic movie plot where you have the overly literal robot that just can't understand how humans think because he always thinks so literally. That's how computers are, right? They can only digest the information that you give to them. And matrices give us a way to take something visual and kind of like something we wave our hands around. Like I kept wanting to take the picture and physically move it for you. If I had a different camera, I could do that for you. I wanted to be able to talk with my hands and show that information. It gets a little bit confusing when we're trying to just talk about it with words. Matrices allow us to take that visual experience and turn it into data, raw, kind of boring data. But I could teach a computer how to make a 270-degree rotation by saying, take the x and y, flip it, and make the y 0. So you don't need to do any more of the, I have your worksheet in front of me here. You don't need to do any more of exercises 1 through 11. I mostly wanted you to see what that looked like during the video, but I want you to complete the information for 12 through 19. So that second part of the worksheet is what I want you to complete. And that should do it for lesson 4.